All right. So it is 3:30. We can go ahead and get started. Yeah, so hopefully everybody was able to get my email reminder that I sent out a few hours ago. But I have indeed set up the checking Tuesday emails to go out at 4:30 during today's class. I will double check that that actually is going out. I have my email pulled up now. So at 4:30, feel free to stop me and remind me just to double check that those emails are in fact going out. But like I mentioned, regardless of whether or not you have been selected for the Checking Tuesday, you will receive an email basically telling you which scenario it is essentially. So if you didn't receive an email, you can let me know. But yeah, generally speaking, yeah, about 8 people in the class have been selected. And yeah, so if what I would suggest is at 4:30, we'll stop for like a few seconds just for you guys to take the opportunity to check your emails. And if you, in fact, do see that you have been one of the people who has been selected, what you should do is log off of the lecture. Basically, carefully read through the instructions that have been given to you in the email. And then basically you have 20 minutes to read the attached PDF file that is in the email and create a less than 10-minute video, essentially explaining your answers to the particular questions in that assignment or in that check. And also, just as a reminder, the question will look very similar to a question that you just submitted in homework assignment 2. So generally speaking, if you put forth a good faith effort to try to, at the very least, understand what you put down in assignment 2, then you should have nothing to worry about. And again, we're not necessarily checking to see that you got the right answer to this check, but more so that you can articulate your thought process for, whatever particular answer that you have arrived at. So do make sure that, you are meeting all the specifications of the video. So that can essentially be one of the key ways that you might end up losing points, which would be unfortunate. So you do want to make sure, again, you have your camera on, your mic is on, you're sharing your full screen, and you're not using any of the materials that you're not supposed to be using, essentially. So you can use your notes, you can use Google, and you can use, I would highly suggest using your previously submitted homework assignment, but allowed to, go on ChatGPT. You're not allowed to, talk to any of your classmates. This should be your own work, essentially. Okay. And then, yeah, you want to make sure that you are submitting that, the link for that Zoom cloud recording to Canvas by the deadline. Otherwise, we will have to take off points for that as well. All right. So any questions on that? Yeah, I see hand raised. I'm guessing this is probably for what you put in the chat here. Yeah. So I did post. Oh, so go ahead.
I'm sorry. I just have a quick question, two questions actually.
Okay.
First question about the polls, and then the second question is when we speak about the Zoom recording,
Mhm.
uh, is it okay just to use like the regular Illinois Zoom account, right? And then whatever the link it will give you, because this link we have to submit it to the Canvas, right? Not to the media space, because I saw in your instructions in Canvas, you mentioned something about Illinois media space, and now I'm hearing about Zoom, so I'm a little bit confused.
So it should be submitted from the Zoom recording link that is provided. So I would say follow the instructions that are given in the email. But yeah, I would suggest, when you're creating that recording, use your Zoom Illinois account, in which there's an option for you to record to the cloud. And so the nice thing about recording to the cloud is that even though the video is not yet compiled, you still are able to share that link even before it's compiled. So basically, once you finish that recording and shut down your Zoom meeting that you've created, the corresponding Zoom meeting recording will show up in the Zoom recordings URL. And so you can share that link with me, even though the video has not yet compiled. And this essentially enables us to quickly submit a recorded video in a 20-minute time window, essentially. Okay.
So thank you.
Yeah, and then the poll is in reference to this warm-up question here. So I think what I'd like to do is actually open up a quick breakout room just for you guys to discuss this question here. So I've just opened up the breakout rooms and you can share your screens. But yeah, bullet point is essentially what I've done here is I've created a clustering of 3 objects. So, oh, sorry, hold on one second. Yeah. Yeah, we're good. So objects 2 and 3 are in one cluster and object 1 is in another cluster. And so what I'm asking is it possible to create another clustering of these same 3 objects such that the RAND score between these 2 clusterings is exactly equal to 0? And think about why or why not that might be. Okay. So I've just opened up the breakout rooms. You can choose your own room. Chat about this for a few minutes, and then we'll meet back and discuss. Okay, so everyone should have been assigned. So if you can go there now, we will meet back and discuss. Okay, so welcome back. I'll let people trickle back in over the next few seconds, but yeah, if you have changed your answer to the poll based on what you discussed in your breakout rooms, you can do so now. So it seems like everybody's sticking to their guns, to their previous answers. Okay, so I will shut the poll down now. Okay, so pretty even distribution roughly of people that say yes, people say no, and people that say they are not sure. So, any opinions as to why or why not, or why it is or is not possible to create a clustering that has this particular specification? Realize that this is a little bit more involved here in terms of like explanation. But yeah, this is essentially what we want to do here. We want to come up with a clustering or a second clustering of this data set such that the RAND score of these two clusterings has a RAND index value of exactly 0. So you want to remember that the denominator of this expression simply just represents all possible pairs of objects that exist in the data set. So that would be, and that's something that ultimately is not going to be able to change in terms of its sum. That's simply just 3 choose 2, which is equal to 3. However, what we can in fact change is the sum in the numerator. So in order for this overall fraction to be equal to 0, what we would need to have happen is for our f11 to be equal to 0 and our f00 to be equal to 0 as well. So what that means is we can have no pairs of agreements essentially between the observations in clustering 1 and observations in clustering 2. So what that means is that if two observations are together in clustering 1, then they must be apart in clustering 2. And similarly, if two observations are apart in clustering 1, then they must be together in clustering 2. Okay, so observations 2 and 3 are together in clustering 1. So what that means is that they should be apart in clustering 2. Then observations 1 and 3 are apart in clustering 1. So what that means is that they should be together in clustering 1. And similarly, observations 1 and 2 are apart in clustering 1. So what that means is that they should be together in clustering 2. So based on these specifications here, is this possible? Is it possible to create a clustering 2 that meets everything that we just stipulated here? So basically, we're seeing when it comes to creating a clustering, there's essentially a rule of transitivity going on here. So we said that if this clustering is to exist, and again, we want to specify that we are setting up a partition-based clustering or an exclusive clustering in which each observation belongs to one and only one cluster. So given that, this set of specifications that we've set up here is actually impossible. There does not exist a clustering that can be made in which 1 and 2 are together, 1 and 3 are together, but 2 and 3 are not together. Okay, so this is an impossible clustering to make. Basically, if this is to be a partition-based clustering, if 1 and 2 are together and 1 and 3 are together, then 2 and 3 must also be together. Okay. All right. Any questions on that? All right, cool. So we're going to move on from Unit 3, which was talking about various different ways to go about evaluating a given clustering. And we're going to move on to honestly one of my favorite unsupervised learning techniques, because while it is technically, we're going to switch gears for a second, it's technically a dimensionality reduction algorithm. It's specifically used to help us evaluate what is going to be the most appropriate clustering algorithm to use, as well as it allows for us to evaluate various properties about the clustering structure of a given data set. And it also allows for us to help build corroborating evidence that a clustering algorithm that we've applied to a given data set is in fact returning meaningful insights, if you will. So we're going to go back to our eBay auction data set that we have been exploring in previous units. And again, we want to remember that our overarching goal here is to first cluster the numerical variables. And I do apologize, I have a little bit of a cold today, so it's voice is maybe a little bit scratchy here. So we want to cluster the numerical variables into however many clusters are most suitable, or hopefully into however many inherent clusters that exist in the data set. And we want to ask ourselves the following research question, or perhaps the following research goal. So we want to determine the nature of the association between ultimately the clustering structure of the numerical variables and the pre-assigned class labels, i.e. whether the auction is normal or abnormal. So in Unit 3, we discussed a supervised clustering evaluation metric for essentially providing one and only one summary statistic that answered this, or that pursued this research goal for us. So what was that? What was one of those metrics that we could have used to answer this research question or pursue this research goal? If we wanted to evaluate the strength of the association between, let's just say, a clustering and a set of pre-assigned class labels, what is one metric that we could use? So we just talked about it. Well, we could use the RAND score, or we could use the adjusted RAND score, or we could use the Jacquard index. So all of these are metrics that allow us to assess how similar two partitions are to each other. So one of those partitions could be a clustering, and one of those partitions could be a set of pre-assigned class labels. However, these metrics really only provide us one and only one summary statistic for evaluating, essentially how associated those two partitions are. Ideally, we'd like to learn more about, what is the nuanced relationship between each of the, clusters and each of the class labels. So we might be curious to know, for instance, is one of these class labels, or excuse me, is one of these clusters more or less comprised of, let's just say, normal auctions? Could it be the case that one of these clusters is more or less comprised of abnormal auctions? So these are all additional insightful follow-up questions that we might want to learn, that are drilling down a little bit deeper into what is in fact the actual nature of the association between a cluster ring and a set of pre-assigned class labels. So that's something that the TS&E algorithm and the TS&E plot will be able to help us evaluate in a much more nuanced way. So that's one of the benefits that it brings. So I think we're going to skip over this data set here, but I think I'll probably skip over this here as well. So basically we have, as we've been introducing the algorithms, the clustering algorithms that we've talked about so far, as well as the clustering evaluation metrics, we have been running into a lot of open-ended questions that we have yet to really provide useful answers to, right? We have a list of outstanding issues, if you will. So one such issue is that, our first question before performing any type of cluster analysis is to first determine if the data set is in fact clusterable. So one of the techniques that we discussed was using, the k-means elbow plot to determine if the data set is clusterable. But what were some of the drawbacks of using simply just k-means elbow plot to determine if the data set is in fact clusterable or not? Yeah, so it's not reliable for all data. Exactly. So the k-means elbow plot, for instance, and again, we talked about that there's actually many different types of elbow plots that we can create. But for instance, the k-means elbow plot is only designed to detect clusters and therefore clusterability in data sets in which k-means, or it's only able to detect clusters that k-means itself is designed to detect. So again, if we are dealing with, for instance, a set of clusters that are, for instance, non-convex and not well separated or nested in this particular way, k-means elbow plot is going to suggest that this data set perhaps is not clusterable, or at the very least, it does not have clusters that k-means is able to detect. So, the issue is, well, okay, if you knew ahead of time, right, that your data set did in fact meet those ideal properties that k-means, generally speaking, is best able to determine those clusters in, then you would not really have a problem with this. But if you knew ahead of time that your data set looked like this, then you would know to use a different method for A, determining if your data set is clusterable, B, which clustering algorithm to use, and C, what clustering evaluation metric to use. But the problem is, that's kind of the point of a clustering algorithm, right? We don't generally know ahead of time what the, for instance, shapes of the clusters are. We don't know ahead of time, how many inherent clusters actually exist in the data set. We don't know ahead of time, what the sparsity of the clusters are. So the question is, what is one potential method that we can use to perhaps get a sense as to which of these ideal k-means clustering properties are met and not met? So let's actually go through each of these properties one by one and first determine, which of these properties do we, could we figure out ahead of time and which ones could we not, given the tools that we know now. So the first specification or ideal property is that the attributes should be numerical. So this is obviously easy to check. No big deal. Okay. And the second ideal property is that your data set should not have a lot of noise or outliers. So what we saw is that sometimes when using k-means in the presence of noise or outliers, what can happen is perhaps one of the centroids ends up getting dragged out in the direction of outliers, thereby creating all these like singleton outlier clusters. Or in the presence of noise, it's possible that your centroids no longer, become effective representatives of the density-based clusters that you're actually looking to summarize. So we do have some techniques for identifying outliers in a given data set. So for instance, we can go back to some of our intro stat techniques when it comes to looking for outliers that simply present themselves in, by just inspecting a single variable. So you can look at each single numerical variable in your data set one at a time, and we can use that rule of thumb specification that says, an observation is an outlier if it is greater than Q3 plus 1.5 times the IQR, or it is less than Q1 minus 1.5 times the IQR. But the question is, let's just say there's an observation that exists between these two bounds here. And so my question is, I'm going to post a poll. Is it possible that that observation could still, in fact, be an outlier? So I'll say it again. The observation exists between these two bounds. Is it possible for that observation still, in fact, to be an outlier? Okay, try to submit in the next few seconds. Okay, the most of us say yes. And yeah, there's actually a wide variety of ways in which an observation can manifest or showcase itself to be an outlier. So one such way is by simply just looking at the relationship between two variables. So for instance, you could have created a scatter plot visualizing the relationship between two variables in the data set. And let's just say you had a bulk of observations that existed around here. Oops. And let's just say, for instance, you had a observation that presented itself around here. So this observation is, in fact, an outlier. But if we were to, for instance, create a corresponding box plot, let's just say for the y-axis, maybe let's move that point a little bit closer here, something like that. Then that point, in all likelihood, would in fact show up within the box. Most likely it would not be counted as an outlier. And then the same thing would happen, if you created a box plot for the x-axis values like this, something like this. More likely than not, that observation would also not show up as being an outlier when examining just a single numerical variable like x. But we see that when we look at the relationship between two numerical variables, it does in fact present itself to be an outlier that we would not have detected simply just by examining our single numerical variables one at a time. So one strategy that you could use is to create a scatter plot for every pair of numerical variables in your data set, and that would be another pass that you could give to your data set when it comes to looking for outliers. However, unfortunately, maybe you can see where this is going. It is entirely possible for there to be outliers that only showcase themselves to be outliers when looking at the relationship between 4 or more variables in the data set. It's because it's not possible for us to visualize a 4-dimensional scatter plot by simply just using these techniques, like looking at the relationship. Essentially, we're unable to detect the presence of those additional outliers that might exist. Okay, so because it's not possible to examine a 4D scatter plot, there may be additional outliers in the data set that only present themselves in examining the relationship between 4 or more variables. Thus, we would not be able to see it or identify these outliers. Okay. So one of the benefits of some of the clustering, as well as clustering evaluation techniques that we're going to learn in this class, is that there are, in fact, going to be sophisticated ways for us to go about looking for these additional outliers that might exist in the data set, but don't immediately present themselves when looking at like box plots and scatter plots, if you will. But so the downside is still, nonetheless, is that if we plan on using the k-means clustering algorithm to identify our clusters that exist in the data set, if we don't know how many or if there are outliers ahead of time, then it's possible that our k-means clustering algorithm may give us or may yield performance that we're not essentially looking for, or might, provide clusters that we are not in fact looking for. And in addition, our clustering evaluation metrics, for instance, like the silhouette plot, may lead us to believe that some clusterings are better than others, when in fact, the ultimate clusters that we're looking for, i.e., something like this, may not in fact actually be discovered or suggested by those clustering evaluation metrics. So unfortunately, we don't really have a foolproof method of determining all of the outliers that might exist in our data set. So that is currently a problem that we have. Now, in addition, we also talked about, in order for k-means to work most effectively, or in order for it to most likely be able to identify the inherent clusters that exist in the data set, you need to know the correct or the inherent number of clusters to ask k-means for. So what are some of the techniques that we've discussed that can suggest how many clusters inherently exist in the data set? Yeah, so we talked about the k-means elbow plot method. And then what's another technique that we just discussed last week? So it was similar to the k-means elbow plot, right? And that on our x-axis, we had a bunch of k values. But then what were we plotting on the y-axis? So we're not yet at, we haven't quite discussed using a dendrogram yet. So a dendrogram looks for nested clustering relationships. So, but yeah, I mean, that is one way that we briefly discussed. But yeah, what we more in-depthly discussed in Unit 3 was using the average silhouette score plot method. And, the way that we used that method was essentially we chose the clustering and the cluster numbers that had the highest average silhouette score. But unfortunately, there were also some downsides to these two techniques when it comes to selecting the right number of clusters to ask for. So what are some of these downsides that we discussed? So some of the downsides that we discussed, for instance, is that the silhouette score, or the average silhouette score, if you're using the Euclidean distance metric, measure the distance between 2 points, it tends to only be effective, or tends to be most effective, when evaluating the cohesion and separation of what type of shapes? Convex, yeah, that's right. Convex cluster shapes. And so unfortunately, the downside is if we don't know what our cluster shapes are ahead of time, then we don't know if the average silhouette score is going to be an effective way, to go about selecting the right number of clusters. And in addition, also one of these downsides is we, regardless of whether we're using the k-means elbow plot method, or let's just say we're using the average silhouette score plot method, we're bound to essentially using an algorithm. So maybe it's k-means, maybe it's something else. We're bound to using an algorithm to look for a clustering with k equals 1, 2, 3, 4, however many clusters. So unfortunately, both of these methods are algorithm dependent. We iteratively cluster the data. K equals 1, 2, 3, clusters. Using particular clustering algorithms. Okay, so unfortunately, maybe it might in fact be the case that there exists some other clustering algorithm that is the most effective one at identifying the actual clusters that exist in the data set. But if we're not actually using those clustering algorithms, to calculate the inertia in the elbow plot method or calculate the average silhouette score in the average silhouette score method, then both of these methods that we're using to determine the right number of clusters is going to be potentially missing out on, essentially using the clustering algorithm that is most likely to detect those clusters. So basically, because we don't actually know, what the shapes of our clusters are, or in other words, if k-means is in fact the most effective clustering algorithm to use for our cluster shapes in our data set, then we can't fully trust that these evaluation metrics for knowing the right number of clusters to ask for is in fact going to be the most effective evaluation metrics. Okay, so still a lot of open questions. I'm going to put again a question mark next to this part here. Okay, now in addition, we've also stipulated these 4 other ideal properties that we really have no sense, we haven't even really discussed how we might go about determining, if these are in fact the case. So 1, in order for k-means to work the most effectively, we need to specify that, or we ideally need for the number of clusters to have roughly the same number of objects. So we really haven't discussed any methods so far that give us a sense as to how many observations belong to each of these inherent clusters. 5, ideally, each of our clusters will be spherical. And so again, we really have not discussed anything so far that determines, the shape of these inherent clusters. 6, whether there is good separation between the clusters or not. So we don't really have any sense as to, if that's the case or not yet. And 7, ideally, the cluster should have the same sparsity. So we don't really have a sense as to how to even go about evaluating these final 4 properties. Now, the nice thing about the TS&E plots that we're going to introduce in just a second is that it actually gives us a way of assessing what the right or inherent number of clusters might be, about how many observations belong to each of these clusters, the shapes of the clusters, as well as how separated those clusters are. And in addition, it also is going to give us one potential way of simply just evaluating if the data set is clusterable or not. And the cool thing is, unlike some of these other techniques that we've discussed up here, like the k-means elbow plot method, the TS&E algorithm and the corresponding TS&E plots are going to be clustering algorithm independent. So the clusters that we are going to be identifying, or the clusters that are suggested by these TS&E plots, are not going to depend on the particular clustering algorithm that we are currently considering. However, I do want to give a big caveat here. First, though, all algorithms that deal with clusters have their own implicit assumptions about what makes for a cluster. Okay. So even though this TSNE plot method is not going to be dependent or reliant upon you pre-selecting like, k-means, k-metoids, k-medians, this TSNE algorithm is in fact a algorithm, right? That will have some sort of embedded assumptions about or basically it has its own embedded assumptions about what makes for a cluster. So it is possible, just like we've seen with other actual clustering algorithms, that this TSNE algorithm, which is actually a dimensionality reduction algorithm, will in fact make assumptions that unfortunately make it unable to detect some clusters that exist in some data sets. So basically, there's always downsides to every algorithm that we're introducing here. So you want to be mindful about what those downsides and what those assumptions are. Okay. All right, I think I've been doing a lot of talking. Any questions on that? Okay, and somebody do remind me when it hits 4:30, just so I can double check the emails went out. All right, so generally speaking, what I like to do is I like to give a brief overview of how the TSNE algorithm works and how TSNE plots work at the beginning of the semester, because they're an extremely useful tool when it comes to evaluating our clustering algorithm results for each of the new clustering algorithms that we'll talk about in the class. Usually on the second to last day of class, I'll dig a little bit deeper into the math of how the algorithm works in particular, but I like to introduce just a general overview of how it works up front, just so we can really start getting our hands dirty with, using this algorithm and really learn how effective it can be when it comes to essentially aiding our cluster analysis. Okay, so basically the end result of the TSNE algorithm, which stands for T-distributed stochastic neighbor embedding, is what we call a TSNE plot. Now, this TSNE plot is usually either a 2 or 3-dimensional scatter plot. Okay. Now, the thing that you want to remember here is that the TSNE algorithm, while it is used to aid a cluster analysis, it is not actually a clustering algorithm in and of itself. Rather, it is a dimensionality reduction algorithm. So its overall goal, just like with any dimensionality reduction algorithm, is to take usually a high dimensional data set and project it or represent it on a 2, or in our case 3, lower dimensional data set, while preserving some aspect of the original data set. So the key way to distinguish between all of the different dimensionality reduction algorithms that exist in the literature is to think about what aspect of the original data set is the algorithm or model trying to preserve. So when it comes to the TSNE algorithm, what implicitly the algorithm is trying to preserve is the clustering structure of the high dimensional data set. Now, the clustering structure is not actually the explicit element of the original data set that it's trying to preserve, but it usually has this nice effect that many aspects of our inherent clustering structure do in fact end up getting represented in the 2-dimensional plot. So actually the key thing that we are actually trying to preserve from the original data set is the following relationship that exists between pairs of points in the original data set. So the key assumption for the TSNE data projection is that if 2 observations are considered neighbors in the high dimensional data set, then they should be neighbors in the low dimensional data set. Okay. And so when we select the parameters for the TSNE algorithm appropriately, what we can do is we can take this high dimensional data set, project it onto this two-dimensional data set, and in so doing, if we're able to basically preserve the pairwise neighbor relationships of observations in the high dimensional data set, what we can actually end up seeing is in fact a suggestion of what the inherent clustering structure looks like in the high dimensional data set in the resulting TSNE plot. So for instance, here are some properties of the original data set that we may be able to interpret with an appropriately created TSNE plot. So basically the key thing here about the TSNE algorithm, it's very powerful, but you do need to make sure that you are selecting your parameters appropriately. Otherwise, your results can lead to very misleading interpretations about the data sets. We'll talk about how to select those parameters this week, basically. But the cool thing is, or one cool thing that you can identify from a resulting TSNE projection is whether or not there exists a clustering structure in the high dimensional data set. So if you've selected the right TSNE plot, if you see a clustering structure in the TSNE plot, then what that can suggest is that there is a clustering structure in the high dimensional data set. So I will tell you now, I have in fact selected the appropriate TSNE plot for this high dimensional data set here. So what this first tells me is that, yeah, I see 4 clusters. So there is in fact, there is a clustering structure to the high dimensional data set. All right, so that's cool. In addition, the TSNE plot, when selected appropriately, can also tell you a little bit about the nature of some aspects of the inherent clusters that exist in the data set. So for instance, it can give you an approximation of the number of clusters that inherently exist in the data set. So for instance, I see 4 clusters in this TSNE plot. So that can be a suggestion that there are in fact 4 clusters in the high dimensional data set. It can also give you a suggestion as to the number or to the shapes of the inherent clusters. Now, the interpretation of the shapes in the TSNE plot does require a little bit of finesse. So it's like you need to kind of make an executive decision as to how much of the local structure that you should be focusing on versus the global structure. So by focusing too much on the local structure, it is possible to get a perhaps misrepresentation as to what the shape of these clusters actually look like. But generally speaking, if you focus on more of a global structure of what you might see interpreted in these shapes, you might come up with a suggestion that there are perhaps 3 roughly ellipsoidal clusters. And then maybe it's possible perhaps that this cluster might be convex. But basically, what you're going to see here is that in this TSNE algorithm, this is going to be a non-deterministic algorithm. So basically, for different random states, you will in fact get different results. So one way to clarify your doubts as to what the shapes actually are, based on how much you should be focusing on the local versus global structure, is to generate more TSNE plots using more random states. The more often that you see the same general structure of the shape, the more confident you can feel about what that shape actually is. So for instance, I might interpret for now that this might suggest that the original data set has 4 clusters. 3 are roughly ellipsoidal. 1 might be non-convex. Okay. It can also give you a suggestion as to the number of objects that exist in each cluster. So, we can use more sophisticated techniques, if you will, to, we can use row filtering, to isolate these observations here in the given data set or in the given projection and, count up how many observations belong to this cluster. But we can roughly see, without, putting in too much work at the moment, that these 4 clusters are roughly balanced in size. Okay, so having a sense as to how many clusters exist in the data set, this is good for k-means. Unfortunately, given the fact that these 4 clusters are not spherical or suggested to be not spherical, this is not ideal for k-means. However, given the fact that these 4 clusters are balanced in size, this does, in fact, meet one of these ideal properties for k-means. So someone's asking, is the random state just the seed? Yes, that's right. Yep. So generally speaking, when we're creating these TS&E plots, it's a good idea to fix a couple different random states or random seeds for reproducibility. And finally, another thing that the TS&E plot can suggest about the high-dimensional data set is whether or not the inherent clusters are well separated or not. So again, if you have selected the right TS&E plot with the right parameters, then you may in fact interpret that given these 4 clusters that we see here with our eyes are in fact well separated, that might also suggest that the 4 inherent clusters in the original data set are also well separated. Yeah, so someone's asking, is it possible for the different random states to suggest different clusters or different sizes? So yes, it's possible that if you have not selected an appropriate set of parameters, so in particular, this perplexity value that we're going to talk about very soon, it's possible that some of your results may change. Now, because of that, it's never a good idea to interpret one and only one TS&E plot. The interpretations that you gain from the TS&E algorithm should be based on your aggregation of what you have examined across multiple random states and across multiple parameter values, in particular, this perplexity value. Because it's actually going to be the case that some perplexity values will, in fact, not effectively be able to reveal the inherent nature of the clustering structure. So we're going to talk about how many plots would be adequate as we move on to the later parts of the units. But yeah, these are all good questions here. So some additional things that the TS&E plots can suggest for us if we've selected the right parameters is, for instance, to help us more effectively answer a research question such as this. So for instance, not is there an association between the clustering structure of the numerical variables and the pre-assigned clusters, but we can actually ask a more nuanced question. That is, what is the nature of the association between the clustering structure of the numerical variables and the pre-assigned class labels? So what we might do, for instance, is color code the points in our TS&E plot by these class labels. And if this scatter plot, or if in fact this TS&E plot does faithfully represent the nature of the clustering structure, then what we can see here is a much more nuanced description as to how the class labels relate to the 4 inherent clusters that exist in the data set. So for instance, we might see here that 2 clusters are completely comprised of normal auctions. And we might say the other 2 clusters are half abnormal and half normal auctions. Okay. So this gives us more nuanced insights that the RAND score, or the adjusted RAND score, was not able to tell us. So the RAND score simply just gave us a single number that evaluated essentially how strong that association was between the clustering, let's just say found from k-means, and the class labels. Okay, so more nuanced insights is always a nice thing to have. And finally, you can use the results of the TS&E plot to help build further corroborating evidence that the clusters that you found in an algorithm such as k-means are in fact meaningful, however you decide to essentially define meaningful. So one of the nice things about the TSNE algorithm is that if you have selected the right parameters, or more importantly, the right perplexity value, it can be effective at basically demonstrating whether or not there exists meaningful separation between sets of observations in the data set. So like we mentioned, it's certainly possible for us to take a blob of observations, cluster it with k-means, and unless we're being careful, for instance, unless we're like checking a k-means elbow plot, it's entirely possible for us to kind of, return a set of cluster labels for a given data set like this, and perhaps mislead people into thinking that this data set actually looks more like this, where there exists this inherent separation between the clusters. So the nice thing is, because the TSNE algorithm and the TSNE plot is more effective at showcasing inherent separations that exist between sets of observations in the data set, you can color code your coordinates that you found from the TSNE algorithm for each of the observations by their corresponding k-means cluster labels. And this can, in essence, provide an additional layer of corroboration that the k-means cluster labels that you actually found do, in fact, look more like this, as opposed to something like this. So for instance, I can see that all of my k-means cluster labels too, for the most part, except for this observation here, are in fact well separated from all of my k-means cluster label 0 observations. So what this might tell me is, because most of my k-means clusters are showing up as well separated in this carefully selected TSNE plot, this suggests that there does exist an inherent separation between the clusters that k-means identified. Okay, it is 4:30, so let me just double check that those emails went out. Let's see. All right, there we go. Okay, so I'll give everybody about 30 seconds to check your email to see whether you have or have not been selected. And again, if you have not been selected, you should definitely stick around in the class, because I will start teaching again in the next 30 seconds. If you have been selected, do log off the Zoom room now and follow the instructions in the email. And again, if you get stuck, if you run into any technical issues, Jordan is standing by to assist you. So he's going to be checking his email pretty consistently over the next 20 to 30 minutes. So yeah, so I'll let you guys go now for those of you who have been selected. And again, no pressure. Again, not looking for the right answer, but just more that you can articulate your thought process. If you have any issues that you experienced, definitely let me know as well, and we can discuss backups essentially. Okay, so I'm going to assume that those people who have been selected have logged off, and so we will get back to Godspeed. Get back to what we were talking about here. Okay, so these are the cool things that a carefully selected TSNE plot can in fact suggest to you about the data set. So let's learn a little bit more about how this TSNE algorithm actually works. So how does it create these super effective projections of high dimensional data sets that ideally preserve the clustering structure? So one of the specifications for the TSNE algorithm, or at least the original TSNE algorithm that we're going to be exploring in this unit, is that your data set should be purely comprised of numerical attributes. Now, we will discuss a categorical and a mixed data type analog for the TSNE algorithm a little bit later, but for now, we're just going to focus on examining the clustering structure of a numerical data set. So there's a couple of parameters that you do need to think carefully about when it comes to running this algorithm. So number one, you want to think about how many dimensions or how many columns, if you will, do you want to project your original data set onto? So we usually select two because visualizing a data set with a two-dimensional scatter plot tends to be the easiest, but you could select three as well. Now you can also select the number of iterations that the algorithm takes. So basically, the TSNE algorithm is, in fact, just like k-means, going to be a heuristic algorithm that we use in an attempt to find an optimal solution to a optimization problem. So we're going to discuss that optimization problem in just a second. But given that we are, essentially using a heuristic algorithm, usually it's a good idea to specify the number of iterations that you'd like to go through until you basically stop with the best solution that you currently have. And this is just in case the algorithm does not converge to a local minimum in that time. So generally speaking, Python tends to be pretty good with setting the maximum number of iterations for this algorithm. It automatically sets it to 1,000. Now, generally speaking, like the more iterations you include in your, or the more maximum iterations that you include in your algorithm, the more likely your resulting plot is to converge, not necessarily to the same solution, but at the very least to converge in terms of the suggestions that it's making. So it might not ever be the case. So for instance, you might be, running the algorithm for like 1,000,000 steps. And it might not be the case that your particular points will ever show up in the exact same location. But generally speaking, as you continue to run the algorithm, what will generally converge is, for instance, the shapes of the clusters that you end up seeing, whether or not those clusters are well separated, roughly the number of observations that are assigned to those clusters. So generally speaking, the number of iterations tends to be not as important as the following parameter that you need to pre-select. So this is the perplexity. So when it comes to running the TSNE algorithm, the perplexity value is the most important parameter that you need to tune. Now, in addition, there's usually not often one perplexity value that is the best overall for getting the best results. So like I mentioned, when it comes to interpreting a TSNE plot, it's actually best to try out a variety of different perplexity values, usually ranging between 5 and 50. Okay, and this is suggested, this range here is suggested by the researchers that created the algorithm, basically for extracting the most meaningful insights from a given data set. Okay. Now, basically, what this perplexity value actually represents is our best guess or assumption about the number of close neighbors that each point in the data set has. Now, less directly, what this perplexity value essentially does is it allows for us to balance the attention that the TSNE algorithm is placing upon identifying the global structure, in other words, the overall shapes of the clusters, the nature of the clusters, versus the local structure of the data, i.e., whether or not two observations should be close to each other or not. So basically, for whatever perplexity value you set, it's assumed that each observation in the data set will have a number of close neighbors equal to that perplexity value. And so, given that the perplexity value is basically our best guess for the number of neighbors each observation has in the data set, you're not going to essentially get any insightful results, if you will, if, for instance, you set your perplexity value to be larger than the number of observations you actually have in the data set. So generally speaking, your perplexity value should be less than the number of observations in the data set. Okay. Now, based on this assumption, we want to remember what the TSNE algorithm is trying to preserve. So basically, if we have stipulated that two observations are neighbors in the high dimensional data set, then we are also basically forcing these two neighbor observations to be close to each other in the low dimensional representation. Yeah. And so I'm seeing a direct message here because this is a vaguely stated interpretation of what the TSNE algorithm is doing, right? So what counts as close, or how do we know that two, or how do we consider whether or not two observations are close enough to be considered neighbors? And so the answer is actually the algorithm, based on what perplexity value you set that to, will actually force every observation to basically have a certain number of nearby neighbors to it in the low dimensional representation. So based on what we are forcing our dimensionality reduction algorithm to do, we might already start observing a particular aspect of the original data set that may not effectively be preserved in the low dimensional representation. So can anybody think of a aspect of the original data set that we don't think is going to be effectively preserved in the high or in the low dimensional data set? Any ideas? What you remember is so let's just say we've specified the perplexity value to be 5. So what that means is we are assuming that every observation has 5 neighbors in the high dimensional data set. So what that means is every observation in the low dimensional data set will be forced to have 5 nearby neighbors. So is there a particular aspect of some original high dimensional data sets that will not be preserved in the TSNE plot based on this assumption that we are forcing? Yeah. Yes, we're going to run into an issue with outliers. Yeah, exactly. So let's just say we have set of points here, set of points here, and then an outlier here. So this outlier observation, technically, what we can see with our eyes, does not in fact have any nearby neighbors. But what the TSNE algorithm will do is it'll find its 5 nearest neighbors in the high dimensional representation, and it will try, or it'll basically force that observation to be close to those 5 observations in the low dimensional representation. So one downside that we're already seeing here is, for instance, outliers are not preserved in the TSNE plots. Okay, and again, this is because we set that perplexity value to be at least 5. Now, technically, if we'd set that perplexity value to be 0, we would not actually be forcing any observation to be a neighbor of any other observation. But if we set that perplexity value to be too low, then essentially there would be nothing actually forcing, the actual points that you want to remain together from the high dimensional data set to be together in the low dimensional data set. So basically a perplexity value of 0 is going to give you, useless results essentially. Okay. All right. So any questions on that? Okay, so input is your original numerical data set, as well as the carefully selected parameters that you would need to perform parameter tuning on. And your resulting output is simply just going to be the 2-dimensional representation of your high-dimensional data set. Okay, now the main idea of the algorithm is as follows. So basically, like I mentioned, we're setting up an optimization problem that is going to be comparing the distance between our points in the original data set and our points in the projected data set. Okay, so basically, in every optimization problem, there's always a set of decision variables that we're solving for. So our decision variables in this optimization problem are simply just going to be the 2-dimensional coordinates that correspond to every observation in the data set. So ideally, we would solve for this objective function. We would solve for the coordinates that basically minimize this function here. Okay. And so specifically, the way that we go about setting up this optimization problem is as follows. So first, what we do is we create a similarity matrix P for the points in the original data set. Okay. Now we're not going to use the Euclidean distance for pairs of points in this original data set because what we are doing in this particular distance metric that we're using here that we'll discuss more at the end of the semester is we're essentially setting up a very specialized distance function or distance metric that will force the, let's just say, 5 nearest neighbors of every observation to be represented as close, whereas it will force the other observations that are not the 5 nearest neighbors, it will represent the distance between those points as not close, essentially. So the way that the distance metric is defined is actually based on a function, which we can see here actually represents a normalized Gaussian function. So if we want to, for instance, find the distance between, let's just say, observation or the observation that shows up in row 1 and object 2, object 3, object 4, etc., what we would do is we would take a normal curve okay, we would center it at 0. And then we would give this normal curve a standard deviation that flexibly adapts for each observation in the data set. Okay. So basically what that means is that some observations will use wider Gaussian curves and some will use more narrow Gaussian curves. But whatever standard deviation that we end up using for a given point, so basically this Gaussian distribution is going to allow for us to calculate the distance between observation, let's just say x1, and all other observations. Then what we would do to actually find those distances is calculate the actual Euclidean distance between observation x1 and let's just say observation x2. And then find how far up on that Gaussian curve that distance is. And then essentially we would normalize by the sum of all of the basically Gaussian curve heights, if you will, from that we could create in this particular row here. And then basically that gives us the distance between observation 1 and the corresponding observation 2. So basically, if the distance between observation 1 and observation 2 is relatively small, then basically the TS&E distance or measure is going to be considered a lot higher. Or in other words, those two observations are going to be considered more similar to each other because it shows up higher on that Gaussian curve. On the other hand, let's just say, observation 3 is much further away from observation 1. Then if we calculate the TS&E distance between these two observations, then that value does not show up as high on the normal curve, which represents that these two observations, 1 and 3, are less similar to each other. Okay. So higher on the curve equals more similar, lower on the curve equals less similar. Okay, so basically we use this flexibly adaptive Gaussian curve to measure the proximity between all pairs of points in the actual high dimensional data set. And we create this similarity matrix here that we call P. Okay, and the thing here is we want to come up with slightly different standard deviations such that we are enforcing the pre-specified number of nearest neighbors that we have specified for the whole algorithm. So for instance, I would want to create a standard deviation for points in this cluster to be a lot larger because basically the sparsity of this cluster is higher. So basically I would need that Gaussian curve to be more wide for, let's just say, 10 points to be considered high up on that curve. On the other hand, if I was considering the distance or the TS&E distance for points in this more dense cluster, then I would want my Gaussian standard deviation to be a lot smaller. So I was basically forcing, again, let's just say only about 10 points to be considered nearby neighbors or to have a high proximity. So that's another thing that the Gaussian, that the TS&E algorithm will do. While it's constructing this similarity matrix P, it basically finds the optimal standard deviation, which will in essence force the number of nearby neighbors based on this distance metric that we've created here to be exactly equal to the number of nearby neighbors that we've specified. So for instance, if we specified for there to be 5 nearby neighbors, or we've specified the perplexity to be 5, then a pre-processing step of the TS&E algorithm will find the optimal standard deviation that basically forces each of these Gaussian curves to only have 5 observations that are close, essentially. Okay, so I think I've gone a little bit over, but basically this is just step 1 of the algorithm where we create this really intelligent proximity matrix or similarity matrix of the original data set. And then the next thing that we would do is create this also intelligent similarity matrix for the projected data set, i.e. our TS&E coordinates. And then the optimization problem that we end up setting up is to be one in which we calculate or find the optimal decision variables that minimizes the distance between these two similarity matrices. So the distance between our actual original data set similarity matrix and our projected coordinates TS&E coordinate similarity matrix. Okay, so we'll talk more about that on Thursday. So I've definitely gone a little bit over. So I will stop recording